So pairing symmetry, conventional superconductors S wave, cuprate superconductors D wave. But in the first month or so after the discovery of high-frequency superconductivity in the iron-based superconductors, there were a lot of proposals, a lot of enthusiasm, because there are so many bands that cross the Fermi level that there's just a lot of different, there's combinatorially a lot of different possibilities for the pairing symmetry. And here are some figures I borrowed from a paper by Muller, and showing the sign of the order parameter in red and blue. And with all of these different Fermi surfaces, there's lots of different possibilities for the signs of the order parameters. So an outline of the talk that I'm going to give is, I'm going to talk a little bit about possible bulk measures of pairing symmetry, and then argue that STM as a local measure is probably a more viable way to go than a bulk interference experiment. And so I'll give a very long introduction to STM as a real space and momentum space probe, and then talk about STM experiments by Hanaguri, showing pairing symmetry in iron selenium barium, and more STM experiments on pairing symmetry to explain iron selenium. And if I have a little extra time at the end, I have about 10 extra slides on vortices, vortex studies within my own lab. So the pairing symmetry very early on is predicted, among many other things, but phenomenally predicted to be S plus minus, and this is because there can be a nesting vector which matches an anti-ferromagnetic ordering vector in material. So here is the unit cell, here's the crystal structure of material, the iron, and then the pnictide or chalcogenide, which can be either up or down the plane. And so here's like the talk in this unfolded Brillouin zone with one iron per unit cell. But if we look at the actual full tetragonal Brillouin zone with 2 irons per unit cell, it looks like this. And so we folded the corners of the Brillouin zone into this diagonal square here. And now in the spin density wave state, there are fluctuations in all of the materials we know so far. There are at least fluctuations in static spin order, at least fluctuating spin order with this wave vector here, EAF. So it's collinear antiferromagnetism along the irons, and this antiferromagnetic wave vector matches exactly the nesting vector between the hole Fermi surfaces here and the electron Fermi surfaces here. And so this suggests that there's a spin-based mechanism for the pairing between these Fermi surfaces. So if we look at the comparison between the cuprates and the pnictides, I think Tom showed my slide earlier this week too. But in the cuprates, it's plausible that there's a spin-based pairing mechanism because you can have nesting across parts of the Fermi surface like this, and that's analogous to what may be going on in the iron-based superconductors. And so this dates back to some older work. Kuroki pointed out in 2001, and maybe even earlier work, that if you're going to have superconductivity, then your effective interaction here must be positive, or there's a minus sign, so yeah, it must be positive. And this is the sum of the interaction times the 2 order parameters of the 2 participants in the pairing. And so if the spin fluctuation is a positive interaction here, then these 2 must have opposite sign in order to drive the overall interaction positive and allow for superconductivity. And so what that means is that if you are going to propose a spin-based mechanism with a magnetic ordering vector, then the nesting vector, which connects Fermi surfaces at that magnetic ordering vector, must be connecting a positive sign to a negative sign in order for this to give you a positive effective interaction with superconductivity. So that leads to, in the cuprates, a D-wave pairing scenario where there's actually a sign flip on the same Fermi surface here, there's a no wave because the order parameter goes to 0, and in the iron-based superconductors that would lead to a sign flip between the hole pockets and the electron pockets. Okay, so very early on, there were a couple of, actually this was a quite heroic ARPES experiment. They, I think, beat crystals that were 100 microns something on the needle of a pin. That was a beautiful photo. And they were the first to show via ARPES that there was the Fermi surface didn't seem to have nodes. And then there was a later experiment on the 122 materials, once larger crystals were available, showing again, mapping out in more detail, multiple Fermi surfaces, none of which had nodes. So both of these two early experiments seemed to support this S plus minus pairing in which there are no nodes on any particular Fermi surface, but there might be a phase split between the Fermi surfaces, but ARPES cannot provide that phase-sensitive information of whether there's a phase split between the experiments. So it seems like pretty early on there was a lot of convergence on this idea of S plus minus symmetry, but there were also plenty of papers which did give evidence for gap nodes, plenty of specific heat, NMR, point contact spectroscopy, thermal conductivity, penetration depth, many experiments which gave evidence for gap nodes. So the controversy was not resolved just by the ARPES experiments, and there's really a call for phase-sensitive information. So if we look back at the cuprates, in the cuprates, again, ARPES in the early 90s started to show evidence that there were nodes in the superconducting order parameter. So the ARPES gave evidence that the order parameter kind of looked like a clover. So it would be large magnitude in 4 directions and nodal in the other 4 directions. But ARPES, again, couldn't give information about the phase of the order parameter. So in order to learn about the phase of the order parameter in the cuprates, an experiment was done in 1993 with a SWID, corner junction SWID, where YBCO, a single crystal of YBCO, was aligned with a lead ring such that electrons tumbling out along this arm of the lead ring would have one phase if this were a D-wave order parameter, whereas pairs tumbling out of this arm of the lead ring would have the opposite phase if this were a D-wave order parameter. And so if a current is flowed this way, then the pairs tumbling this way and the pairs tumbling this way, when they meet up, are going to interfere. And if you now vary the magnetic flux through this ring, you should be able to sweep out an interference pattern in the currents that passes through the SWID. And so here's a theoretical prediction as a function of applied field in units of flux quanta through this SWID here. If we have an S-wave order parameter, then at zero flux, these two arms would interfere constructively and give a peak in the critical current. Whereas for a D-wave superconductor, these two arms would interfere destructively and give a node at zero flux through this ring. So this is theory here. And now this experiment was actually performed by Dale and Harlian and a group at UIC, and what was found was, so now keep in mind, the top plot is critical current, and the bottom plot, confusingly enough, is resistance. So you have to kind of flip upside down between going from the current plot to the resistance plot. So if this is a D-wave superconductor, we expect a node in the critical current, which would be a peak in the resistance. Sure enough, for this corner junction SWID, there was a peak in the resistance at zero applied magnetic field. Whereas when they made the same SWID with an edge junction, i.e. both arms coming off the same side, they found a dip in the resistance which would correspond to a peak in the current, which is what you would expect for the constructive interference between two arms coming off the same side. So this was a beautiful bulk geometric demonstration of the sign change between the lobes of the order parameter and YBCO, the cuprate superconductor. So now if we think about trying to do the same thing with the iron-based superconductor, here's just a cartoon of the way the pockets are laid out in the iron-based superconductor, and you can see that along any given momentum direction, there are going to be pairs of two different signs. So if we orient our iron-based superconductor like this, we're going to have both signs of pairs going this way and both signs of pairs going this way, so we're not going to have any periodic interference pattern that's easily detectable. And even if we look like this, it's not clear what kind of interference pattern we would get from this iron-based superconductor. So because of the difference in the topologies of the Fermi surfaces, you just look back at this plot here, if you go in any given k direction in this plot, you're going to have a fixed sign. Whereas for any given k direction in this plot, you pass through Fermi surfaces of two different signs. So it's not easy to sort of do a bulk geometric separation of the sign to the order parameter by macroscopically orienting a single crystal of the iron-based superconductors. So I'm going to argue that what we actually need is a local tool, STM, to do a local interference experiment as opposed to a bulk interference experiment. Okay, so here starts the very long introductory part about STM. So a scanning telemicroscope is a scanning probe. It's got a sample. We usually put our sample face down. The tip is pointing up. The tip, we etch it or we cut it with scissors even. And it turns out that under most circumstances, it actually does come pretty close to terminating a single atom. And when you perform some violent electric field pulses on it, and it does, in the end, terminate in a single atom. We scan the tip over the sample and apply a bias voltage between the tip and the sample, typically on the order of 100 millivolts or so. And that causes a current to flow between the tip and the sample on order of 3 picoamps, which we then multiply by 10 to the 9 and measure. And so what does this current correspond to? Well, we typically choose our tip to be some kind of boring material like platinum, iridium, or tungsten, which has a very flat density of states near the Fermi level. And then the sample has some interesting density of states near the Fermi level. So if we just put our tip in proximity to our sample with a zero voltage between them, then their Fermi levels are going to align, and we won't get any net tunneling between the two. But if we apply a voltage between the tip and the sample, then we're effectively raising the Fermi level of the tip with respect to the sample. So if we apply a positive voltage to the sample, then electrons are going to want to tunnel from the tip into the sample, and they're going to be able, energetically, they're allowed to tunnel into all states between the two Fermi levels. So all of these yellow states are available for tunneling into. And so that means that the current between the tip and the sample is going to be proportional to this integrated density of states. So this area shown here in yellow is proportional to the measured current. And what we actually do from an experimental point of view is what we're interested in is this white curve. We're not interested in the integral of the curve, we're interested in the actual curve itself. So you can imagine that you could just sweep the voltage and get the curve by numerical differentiation. That turns out to be not a very clean thing to do experimentally, so we use a locking amplifier to dither the voltage around a fixed value, and then we pick up the dither in the current corresponding to this slim green rectangle, which is at a matched frequency to the dither in the applied voltage. So therefore, in STM, people always talk about DI/dV, the differential current with respect to the differential voltage here. And that differential current is going to be proportional to the density of states at this particular energy sliver here, the little green area. So we do a slow DC sweep of the bias, all the while dithering at this higher frequency and picking up the resulting current at that same frequency. And that allows us to map out this white curve, the density of states in the sample. And now we could also, if we wanted to apply a negative voltage to the sample, and then we would be tunneling electrons out of the sample into the tip. So depending on the polarity of our voltage, we can access both the filled states and the empty states of the sample. Yeah.
If I apply voltages that are very high, assuming like 1 volt or 2 volts, you would travel far away from the Fermi level, right?
Yeah.
Is there any effect by this cascading of electrons to the bottom of the band, to the Fermi level? Is there anything that might happen? You're inserting an electron. You're inserting an electron at an empty state which is far from the Fermi level, and eventually it will go back to the Fermi energy, and then it's kind of.
Oh, you're saying, is it not? Is it a two-step process? Does it go into
Is there anything that will happen in this decay of the electron inside the band, or this can be done?
I mean, people do inelastic tunneling, I guess is what you're referring to, where you can see a step in the DI/dV when a new mode turns on, a new decay mode, energy decay mode. Is that what you're asking?
Yeah,
So,
I don't know that.
Yeah.
Is there any effect? That's my question.
Yeah, certainly people have looked for the bosons in these materials by inelastic tunneling, which is exactly what you say, that there's a two-step process. And so what you would see is a step in the DI/dV. So what people typically do is they set their lock and they look at the second harmonics, they look at T squared I d squared, and they find that step. And so you can measure out the boson modes. And there has been STM work on cuprates, even measuring out those boson. There's a paper by the Davis group in which they measured the energy of the boson modes and then did some kind of O16, 17 substitution, measured them again, and then went back to O16, and they could show that the frequency of the boson modes were shifting slightly in the isotope. And as far as your question about very, very high voltages, when you go to 1 or 2 volts, things get very delicate because, well, A, the tunneling approximation breaks down. The work function is typically, the work function of bismuth is around 4 eV. So you're starting to get close to the work function, close enough that the tunneling approximation breaks down. And furthermore, you risk ripping the bismuth, viscose so fragile, you rip the surface off. Okay, so there's one more factor in this tunneling current here, the differential conductance proportional to the density of states, which interests us, and the distance between the tip and the sample, which doesn't particularly interest us because it's dominated by who's walking around on the floor upstairs, etc. So this is the term that we don't particularly like. It means that the STM experiment is exponentially sensitive to vibrations. So STM is a very delicate experiment. So just a comparison here between momentum spectroscopy and spatial spectroscopy. So ARPES is the workhorse tool for getting information in momentum space. And conceptually they're doing a somewhat similar thing. They shoot a photon in, get an electron out, and by conservation of energy and momentum can figure out the momentum and the energy of the occupied states in the sample. And so their spot size is typically 100 microns or so. So they're averaging over space and getting great detail of momentum space, whereas STM is averaging over momentum and getting great detail in real space. So just examples of the kind of data that are taken with these 2 different complementary tools. ARPES can map out the Fermi surface and the band structure in free one zone, whereas STM can take these beautiful atomic resolution pictures of the surface of this is BISCO, the great superconductor. Every white dot here is an individual BISCO atom. We can even map the superconducting gap as a function of location and find that it varies on a several nanometer length scale. So just to highlight that, for a conventional SWAVE, it doesn't really matter if STM is averaging at the momentum space because it's isotropic to begin with. If you average on a bunch of square wave gaps, you get surprise a square wave gap, a square gap. This is a gap measured on a magnesium diselenide. In a D-wave superconductor, it's a little more problematic because here's just a cartoon of the D-wave gap, which varies in momentum space. Now, if you average a bunch of square gaps of different magnitudes, you're going to get a V-shaped gap. And sure enough, the spectroscopy on BISCO does show a V-shaped gap. So we're losing the information about the different square gaps along these different momentum directions. But STM gets the spatial information, and in particular, what we can do is get a density of states at every single location. I lost this slide on here somewhere. Nope, it's just gone. Sorry. Okay, I can make that point from the slide. So the point is that we have essentially 3 axes of information here. We have 2 real space axes as we scan our tip across our sample, and then we have a 3rd axis of information, which is the energy axis, voltage between the tip and the sample. So we can take these 3-dimensional data sets where we have a full energy spectrum at every point in space, and then we can slice that 3-dimensional data set in different ways. So if we take a single point, this is a point slice at a single location of our data showing superconducting coherence peaks. Or we can look at layers at a fixed energy. So here's an energy of minus 100 MeV, and the IDV map is pretty homogeneous in BISCO at that energy. But if I play a movie where time is running as energy in the corner here, I'm going to start going through the homogeneous region, dipping down, and then going to start to pop back up here, only it becomes inhomogeneous, and I reach the coherence peak at different energies at different locations, and then pop back down, start to pop back down into the superconducting gap. The density of states gets quite low, there's a few atomic resonances, and then I can, yeah, those are some zero bias resonances. Those are probably missing copper atoms. Pop back up the other side, and back to the inhomogeneity of the coherence peaks on the other side. Okay. So in order to make sense of the 3-dimensional data inhomogeneity by reducing this entire piece of information to a single variable, which is the gap, which would take you the distance between the two coherence peaks. There are ways to fit this to analytic forms. There's a Dines formula, which includes both a gap and a broadening parameter. But in general, the fits fail the common sense chi by I test. And so I don't necessarily trust them anymore than the simple extraction of the gap from the distance between the coherence peaks. So here's some examples of gap maps on cuprates, where you can see as a function of doping, the gap is evolving gradually but maintains this spatial inhomogeneity throughout the doping range, passing through optimal doping here. And here's an example of gap maps on an iron superconductor. This is optimally doped cobalt doped barium 122. And both my group and Mark Golden's group have mapped the superconducting gap as a function of location in approximately the same area. And we find similar histograms, although we disagree slightly about the length scales involved. I'm finding a length scale that's more similar to that seen in the cuprates, but both of them on the order of a few nanometers. In any case, there's a lot of disorder in these materials, and I'd like to make the case that the disorder in these materials actually gives us the opportunity to access momentum space after all. After I just told you that we were averaging over momentum space, this disorder allows us to get access to that momentum space. So I'd like to tell this as a little story about how disorder can help us. So this is a picture actually of my college varsity crew team rowing here. And this was probably the nerdiest varsity team at my college, because there's me, and there's Sarah Demers, who's also a physics professor at Yale right now. So I don't know, something in the water there. So there's a picture of the boathouse. Now in front of our boathouse is a bunch of unperturbed H2O. And there's a picture of me, an experimentalist. Suppose I wanted to learn about this H2O, what do? I introduce a perturbation of the H2O and see what happens. And what happens is I get some interference patterns. And if I look at the wave vectors of the interference patterns, I can learn something about the properties of the water, the depth of the water, what's the viscosity of the water, things like that. So I'm going to take that concept and apply it to these materials that I want to learn about, and take a clean material, and then introduce some kind of disorder, such as substitution impurities, or the oxygen dopants themselves. And then when the electron waves, as opposed to the water waves, scatter off of this disorder, they're going to create interference patterns in the same way as the water created an interference pattern in response to this perturbation or oximeter. So the first QPI was done on metals in real space. There's some beautiful images from Cromulus and Igor back in 1993 introducing impurities into the surface of metals. But I want to move back into cave space here and talk about QPI and cuprates and ultimately iron-based superconductors. Suppose we have some disorder potential, then each Fourier component of the disorder will cause elastic scattering between the initial states and the final states whose momentum differ by Q. And the power spectrum of that scattering is going to be proportional to a structure factor of the disorder potential times the density of initial states and density of final states. So this here circled in red is the joint density of states. So in order to see a significant QPI pattern, what we need is a large joint density of states, and you can get that in two different ways. You can get it if you have nested sections of Fermi surfaces, where whole lengths of the Fermi surface are connected by the same Q vector, then you're going to see a large modulation of that Q vector in your interference pattern. Or I just made up a flower pattern here to show that if you have large flat regions in your band structure topography map, then those flat regions contribute a large density of states of a particular energy, and so you can get a lot of interference between these states here. So these flat areas are sometimes called hotspots. So you can get QPI either from nesting or from hotspots. In cuprates, familiar band structure looks like this, and in particular in the superconducting state, if you start at the nodal points and try to build up the band structure one contour at a time, you end up with hotspots, or large flat regions where there's large density of states for interfering with each other at the ends of these bananas. So the density of states is proportional to 1 over the gradient of the band structure, meaning that these flat spots give you a large density of states. And in particular, scattering between any of these is going to give you a large QPI pattern. So your QPI pattern is going to be dominated by the Q vectors scattering between these hotspots. And Q vectors in the map of the density of states. And so if you take then a Fourier transform of your density of states, you should see a map that looks like this. And also, the Q vectors should disperse. So if we look at, here's our V1 zone flat, here's kind of a perspective view of our V1 zone with energy along this axis. The density of the band structure is taking off away from the nodes. So if we look at this particular scattering vector, for example, as we move away from the node, the Q vector is going to get shorter, whereas the density of the energy is going to get larger. So as we move along the energy axis, energy is increasing, Q is getting shorter, and we get a downward slope for this particular Q. For a different Q, Q7, at the nodal point, where the energy is 0, Q7 is also 0, but as we start to go away from the node and increase the energy, Q7 is growing. Okay, so we can then map out the expected trajectories in each of these wave vectors. And if we look at the data, we can see here's the real space density of states, and here's the Fourier transform. So in real space, you can see patterns, but it's hard to pick out multiple patterns simultaneously with your eye. When you Fourier transform, you see the peaks separate, and you can watch each of these peaks, each of these Q vectors evolve as a function of energy. And you can plot then the magnitude, you can fit the magnitude of the Q vectors at each energies, and you can plot the magnitude of each Q vector as a function of energy, and in fact find that they follow very similar trajectories to the expected trajectories for the Q space V1 zone of Visco. And we can map out a Fermi surface that agrees well with our test. Okay, so back to the question of how to detect the sign flip in the iron superconductors. Are there questions about QPI actually, about the technique itself? Yes?
So if I look at your Fourier transform movies that you saw, if I were to not have any information from the octave model or whatever, and I were to just pick out peaks, I feel like I would pick out many, many more than I would expect from the octave model. Or is that just my misunderstanding of it?
I don't actually think there are more. So, so the octave model gives you 7 peaks, which are symmetrized around. So there's 56 of them from symmetry. And if you count them up, you'll see the right number.
Okay.
So each of these, I mean, at point any one of these, I can tell you which one it corresponds to.
Okay.
It does look overwhelming because it's 8 symmetrized there. So yeah.
So but in order to use that procedure, you also need information about the band structure, right?
Yeah. We need qualitative information, and then we can use QPI determinant quantitative information. Yeah. I mean, or you could get a lucky guess, I guess.
So what about if you have some KZ dispersion that comes in? Does this just make this whole picture much more complicated, or can you account for it? Do you know the band structure?
That's a good question.
Or is it
I
simply limited
suppose
to
we would be
2D?
blurring out. I mean, so STM is going to be more sensitive to a higher Z momentum, I suppose. So I think you would be dominated by that part of the KZ dispersion. And there could be some blurring. Is there another question back there? Okay, so how do we use this? So back in the cuprates, we had this global interference. Now in the iron superconductors, because we have the different band structure, and we don't have a single sign for every momentum direction, we need to do a local interference experiment. So now we're going to go back to that equation, the power spectrum and scattering equation. We're going to add one more piece into the mix, which is going to come from looking at the particular type of object that our QPI is scattering off of. So this is the perturbation. This is like Porgo we threw the river. So that's the vortex. So if we look back at the normal metal power spectrum of scattering, it's proportional to the disorder, the density of initial states, and density of final states. For a superconductor, there's this additional term here from the coherence factor of the superconductor. These are the U's and the V's, the unoccupied, and the occupied states. And this is going to have a different sign depending on whether we're scattering off a magnetic object or a non-magnetic object. And these coherence factors for the D-wave superconductor are given by this formula where the gap, D-wave gap comes in there. And so if you just map the coherence factors in the Riemann zone, then you can see that for a two-wave superconductor, they have structure and they change signs at angles. So now if you take this information and throw it into this coherence term here, you'll find that for different Q vectors, this coherence term is going to take different signs. And in particular, different Q vectors are going to react differently to magnetic scatterers versus non-magnetic scatterers. And some Q vectors are going to show up strongly when there are more magnetic scatterers, and some Q vectors are going to show up strongly when there's more non-magnetic scatterers. In particular, because the white regions share one sign and the gray regions share another sign in the Q-gray Riemann zone, these Q vectors are going to be enhanced for magnetic scatterers, and these Q vectors are going to be enhanced for non-magnetic scatterers. But the challenge is, in the material, how to ensure that the dominant scatterers are magnetic or non-magnetic. If you have junk or any kind of unknown impurities, you're not going to know whether you're scattering out magnetic or non-magnetic. So the brilliant idea that Tetsuya Hanaguri had was to use scattering for magnetic vortices. So he took a particular crystal with a particular set of junk in it, and he changed the magnetic field and introduced vortices. So the vortices were the only changing variable, and those were taking the magnetic scatterers based on theory of Chris Coleman, et cetera.
Jenny,
Yeah.
question. So far you talked about point scatterers.
Yeah.
When I go to the vortex, that's roughly a scatterer of the size of coherence length, and these are fairly strongly correlated, so coherence length is a few times lattice spacing, so the corresponding Q is a good fraction of the brilliant zone. So does that change the way I should think about these interference patterns?
So I'm not sure. I know that Chris Coleman has put a good deal of thought into that, and he there's a hidden slide here.
No, it has a structure in D-wave superconductor. It has a structure in D-wave superconductor. The vortex is not.
Well, but,
it's not a round object.
even that's fine. But even if it's a round object, it has a
Yes,
size. Therefore,
yes.
it has a Q.
But if it's not round, it's even more complicated.
Yes.
So this can.
Yeah.
So this is just something I snipped from Chris Coleman's paper, but I think that he's published several papers to put into thought into that.
All right, that's fine. I mean, if I could just.
There's really not an answer to that question in those papers.
Okay. Thanks.
All those coherence factors come from the assumption that the vortex core is a point scatter.
I think so.
And I think they're just some words that, to the effect that, okay, there'll be some smearing, but the overall symmetry of the pattern will remain the same. And I don't think there's anything more than that they really understand.
Well, but I think some of the smaller Qs might completely disappear if the Q is comparable to the 1/, coherence length.
Right, but
I
it's
think
an
that-
empirical question whether you actually see them or not. And if they're seen, then you go ahead with the analysis.
Yeah, I mean, I think
I think it's reasonable. I don't think it's completely well defined, but I think it seems reasonable.
I think the beauty of what Tetsuya Hanaguri did was he did the experiment first on the D-wave superconductors, where the order parameter is well understood to be D-wave, and it's also, there are many Q vectors, and so there's a lot of checks on this. There are 7 different Q vectors, and each of those 7 Q vectors behaves according to the assumption that a vortex is a magnetic point scatterer, I guess.
But
So
there is
it's
also
gonna-
one more part of the story, because vortices, I'm not sure about D-wave, but in S-wave superconductors, vortices also have charge, a real electric charge.
Mhm.
That means that the vortices should also have charge effect, not only magnetic.
Yeah, I've never seen charge in the vortices. If there is charge in the vortices, one should presumably detect it in the topography of the sample. And so it can't be very much, I guess is all I'm saying. It's got to be very low, very, very far below.
The estimate is something like 0.1 electrons. That's a lot. So
I
common
see.
getting for real
But
charge.
it's spread over an area of several nanometers squared, which I guess goes back to the knot.
There was also recent, there was old story, but also recent information in physics. That's a lot of names. Basic physics. Just like this.
Of the charge in
Charge
vortices. Really? Okay, I didn't see that. Thanks.
Just a
With what experimental technique?
It was something connected to my mother, I'm not sure.
With NMR.
I'm not sure.
Okay. So I'm almost done, but yeah.
That's a quick question. Why am I supposed to think about vortices as magnetic scatterers?
I think that's a question for Chris Coleman, I'm sorry.
Well, I mean, basically you assume that the field goes in the vortex core, I guess, for most part. Is that how I should be thinking about it?
But still the
Actually, the
question whether
penetration depth is quite long, so you can't really get the
No,
field.
I think this,
I mean, if there's a spin density wave possibly trapped in the core, that's what neutron stratawaves tell us, right?
But then it's
I thought the vortex was treated as a tau 1 scatter because it's the change of the order parameter which really scatters the quasi-particles.
Okay.
I mean, it's magnetic in the sense that the number scales with the magnetic field, but I think its primary role is to scatter quasi-particles through the variation of delta.
Oh, but wait, but then coherence length has to be essential parameter, unless it's a phase that you take into account, right? I mean, while one can look at it as a phase winding, then it's okay to consider it a point. If we're talking about the suppression of the order parameter, then there is a length scale associated with this gradient.
Well, I mean the Andreev scattering,
Yeah,
so it's the
magnetic
phase.
phase gradient
Yeah.
lumped together.
So it's the phase. It's basically treated as a phase vortex.
So it's a phase vortex,
Yeah.
it's zero core,
Yeah.
just phase
Yeah,
winding.
that's the way it's analyzed. It's just the same coherence factor for both things.
Okay, so on a graded this experiment in NHCCOC, a cuprate where the order parameter is going after D wave, and the expectation was that as the field is ramped up, as the number of magnetic scatters is increased, then these Q vectors will be suppressed, and these ones will be enhanced. And so sure enough, if you look at Q1, if you look at these Q1, Q4, and Q5, they are getting stronger as the field is ramped, whereas if you look at these guys, they're pretty strong here and getting weaker as the field is ramped. And so, so this meets the expectation of the D-wave superconductor. And when the QPI pattern at 11 Tesla was subtracted from the QPI pattern at 0 Tesla, or sorry, the other way around, then exactly the expected pattern was found for the whole area of the sample, where the enhanced ones were seen in red and the enhanced ones were seen in blue and the suppressed ones were seen in red, exactly as expected. So 7 different independent confirmations. Furthermore, Monogori masked out the vortex region and what he calls the matrix region, where there aren't magnetic scatters or aren't additional magnetic scatters, and found very different QPI patterns from these 2 different regions, again confirming that it was the vortices themselves that were enhancing the magnetic scattering. So this is all a proof of the technique, yeah.
So this procedure in dividing locally, it's in the vortex and matrix region. Is it correct that this didn't work for the iron-based superconductors?
It was hard to see the vortices in the iron-based superconductors. I think his samples were disordered enough that he couldn't see the vortices, and he wasn't able to make a clear division between the 2 areas by eye. So what he saw was, let's go back to the iron-based superconductors. So again, there are several Q vectors involved. If you draw a cartoon in which these are perfectly nested, then you have Q vectors connecting these pockets, and these pockets, and some of them should be sign preserving and some of them should be sign altering. So we would expect the blue ones, the sign preserving ones, to be enhanced by magnetic field, and the red ones to be suppressed by magnetic field. So just to prove that he has a nice topography of the surface of, this is iron, selenium 0.4, tellurium 0.6, 13 Kelvin Tc, and he can track the superconducting gap through as a function of temperature. He finds that at the lowest temperature there's a very clear flat bottom to the gap, a square wave gap, indicating that there are no nodes. And now as he changes the field from 0 Tesla to 10 Tesla, there's a clear difference in the pattern. Q3 almost doesn't exist at 0 Tesla and is very enhanced. And let's see, did I get that? Oh yeah, Q3 is expected to be enhanced, right? The blue ones are enhanced. So this is behaving exactly like we expect. So again, according to the vortices and magnetic scatters, and sure enough, Q3 is enhanced as expected, and Q2 is suppressed as expected because Q2 is a sign changer scatterer. So this seems like, if you believe the story in the cuprate, this seems like a demonstration of the phase of the order parameter, the difference between the phase on this pocket and this pocket here, in analogy to the work that was done in the cuprates. And here, admittedly, it's much simpler. There aren't as many different Q vectors to back each other up, but I think the demonstration of the cuprates helps to validate this work in pnictides. So very recently, a couple weeks ago in Science, was published another paper from the same family of materials. This was pure iron selenium, MBE grown, without a single defect in a 100 nanometer field of view, fewer than 1 in 70,000 defects. And yet they saw a V-shaped gap at the same low temperature, 0.4 Kelvin. So this seems to be in contradiction to the S-wave gap seen here at the same temperature, 0.4 Kelvin. And these are the same family of material, iron selenium tellurium, and this one is pure iron selenium. And the fact that there are fewer than 1 in 70,000 defects means that this blurring of the low energy density states, this existence of low energy quasi-particles, can't just be attributed to defect scattering. So there must be something else going on.
What's TC, Jenny?
8 Kelvin in this case.
Thank you.
So
What
how
about
did,
the gas? How did you see?
excuse me?
What about the gas?
2 gas. They, well, you can see their spectra don't go out to very high energy. They didn't comment on this.
No, if you compare the two experiments.
Yeah, so Hanagori's, he didn't talk about the second gap either. So it's out, yeah, he's got a higher TC. So yeah, I guess it should be there, but it wasn't seen in the solid experiment.
And just speaking of the main gas, they are the same magnitude.
Yeah. Yeah. So the reduced gap must be different because the TC is different. So Son postulated that in this material there are actually nodes because the nodal line had cut between the pockets in the tellurium doped material and actually passes through the electron pockets in the selenium doped material. And so we just look at the phase diagram. Here's the Hanagori experiment. Here's the Son experiment. They're within the same phase diagram, but they have very different behavior. And just to note that the tellurium atoms have been shown by STM to be much taller than the selenium atoms. They're bigger, they stick up higher, so you can really see the bimodal distribution of heights here of the tellurium atoms and the selenium atoms. This is from the World Plumbers Group, recently from PRT. And there's a theory by Dunhai Lee, and I think a few others that emphasize this point as well, that the existence of nodes depends sensitively on the interlayer hopping parameter here. And so if you have a large interlayer hopping, you're going to have no nodes, and a low interlayer hopping, you're going to have nodes. And so in particular, for the Son experiment, they have all selenium, which are shorter, smaller atoms, smaller interlayer coupling, smaller interlayer hopping, and empirically they see nodes, whereas for Hanagori they have taller tellurium, which leads to their layers being more closely coupled and larger TZ and node material. So yeah, I think that's it. Thanks.
We have still 7 minutes discussion, so if there are questions. Yes?
So in the one band, in the simple one band model, you basically have magnetic and non-magnetic scatterers. But in the pnictides, you can have intra-band, interband, magnetic, non-magnetic. Is that taken into account in any way?
I don't know how to answer that question. I know another objection that was raised actually in your paper to the second Hanagori experiment was that there's only 3 wave vectors that we care about here, and one of them corresponds to a Bragg vector, so there was some confusion about whether this would be meaningful because of the Bragg vector and the QPI vector mixed up together. And I think the argument that I would make is that the Bragg vector is much sharper. It's can be collapsed, as you know, onto a single pixel, and so I don't think that can explain the entire broad change in that.
I mean, I think that the really important message is the qualitative one. There are a lot of, if you were to try to do a theory of this phenomenon, you could make it arbitrarily complicated and include different scattering amplitudes between different orbitals, and there are many, many things you could include. But the really nice thing about the experiment is that they have the knob that they can turn,
Yeah.
which is to change the number of vortices, and then with one further assumption about the nature of that scatterer.
But I think that's not even an assumption because of the cuprate experiment. I mean, I think the cuprate experiment is so overdetermined. There's 7 different Q vectors there. They all behave as expected with a random field. So I think this is almost proved by experiment without.
I wouldn't go right to proof, but
It's strongly supported by experiment. I take your point here.
yeah.
However, the reason I was asking this question is that I was at a conference, early this week, where people were saying that essentially there were microscopic calculations of precisely that, trying to take into account vortices, multi-band,
they
and they
are.
saw none of this.
Sorry?
In the regulation.
And they saw no suppression with magnetic in the calculation. And the argument was that you only see the suppression if your vortex is close to a defect. Essentially, if you have a pinned vortex on a defect or somewhere nearby, then you see this effect numerically. This is a numerical calculation, so for me it's a black box. Somebody puts something in and tells me what the result is. But for a vortex far away from defect, you didn't see any of it.
But the question here is probably, if I have a question right, is how can you quantify
You mean
the
for
magnitude
vortices?
of the effect
But they did see stuff for impurities.
This is close to impurity.
No, but let's take all the disorder away and
I don't
just
believe that. I
put
don't think I'm going to do that.
tau on scatterers.
The claim was not vortex.
You don't see any of the
You don't see of this.
Did real vortex simulations?
As the cuprates might also here the tendency of spin density wave formation in the vortex course play a role.
Who did this?
Some Japanese.
I see.
Does it play a role in the magneticness of the vortex as a scatter? I don't know. I mean, that's a possibility I said a minute ago. I don't know whether it does. I think that so. So I have. Can I flash one more slide?
In 2 minutes.
2 minutes. Okay. So I'm gonna flash another slide of some interesting results that's new in our lab that I don't understand. But maybe if somebody has some ideas, I'd be interested to hear. So we also did magnetic force microscopy on vortices. And this is old result from Ken Muller's lab, in which she used a magnetic, I was taught on this, but it was named the fear of Hoffman's work, used a magnetic force microscope to drag vortices, and found that in YBCO they drag anisotropically along the different crystal axes. And that kind of makes sense because in YBCO you have these chains, and so the defects which are pinning the vortices are actually chains. But in the iron-based superconductors, there's starting to be evidence that the main pinning defects are really just cobalt atoms or the dopant atoms themselves. And yet, when we did magnetic force microscopy experiments on this 1111 material, and we looked at the anisotropy of the pinning, essentially, we find this fourfold anisotropy of the pinning. And so this is brand new, and I don't know what many people say about it yet, but I'm just interested to know whether it constitutes some intrinsic nature of what's going on in the vortex core, or whether it's some kind of boring aspect of the fourfold symmetry defect.
Where in the phase diagram is this?
Often judged. Well, in these 1111 materials, it's never in a spin density wave phase, except the vortex might induce a spin density wave phase.
Any other questions?
Maybe just a related question, has in any of these materials has been done neutron scattering in the field, let's say in the superconducting regime, in order to see whether the field enhances magnetic response or something like that?
I don't know, does anybody know?
I think we established that there was no evidence for field-induced spin density wave. Is that what you're asking about?
Well, I mean, I wouldn't go that far. Just the question whether low energy response, magnetic response is enhanced. Probably order is not induced. I mean, this is
Yeah.
a strong thing, but
I don't know of any data.
These crystals are pressure.